Hello, my name is Robert Morrow. I am the Chief Operations Officer at Ocean Geophysics. This is a brief presentation, or an attempt to be brief anyway, about the pitfalls of using dynamic coverage. To explain what dynamic coverage is, first we need to talk about surrogate items trials. A surrogate items trial serves multiple purposes. It proves to the client that all the magnetometers are functioning as intended, that the positioning of the vessel's towed equipment is within tolerance, and that the survey parameters, the line spacing, the sensor separation, the maximum allowed altitude are all appropriate, and that conducting the survey with these parameters will produce an accurate representation of the total field residual at a sufficient resolution. So this is the sticking point. It's a problem that we regularly see. It has become commonplace for the survey parameters to be derived from the surrogate items trial. This presentation will show the errors associated with this approach. Ideally, the survey parameters should be derived from a synthetically modeled target of the appropriate volume and shape. The surrogate items trials should confirm that the survey parameters are appropriate, not lead those. We're going to talk through a surrogate items trial, the point of which is to define our survey parameters, and we will show why that is a terrible idea. We're attempting to create a response curve, a graph of response in nanoteslas against spherical range, which is here on the right. A surrogate item of known volume and shape is placed on the seabed in a known position, and a survey line is acquired directly over the target at a recorded altitude. The magnetometer is omnidirectional, meaning that if a survey line traverses directly over the surrogate item, the altitude is the spherical range. So the altitude and the response are recorded. So we shot our first line at 2 meters altitude, 450 nanotesla response. We plot 450 nanoteslas against 2 meter spherical range. And then we shoot another line at a different altitude, 3 meters, and another line. At 4 meters, another line, and another line. And eventually, we end up with enough data points to create this response curve. Once a response curve has been derived, a maximum spherical range from the surrogate item can be determined. This spherical range comes with an associated response in nanotesla. So in this example shown, an 8 meter spherical range, here at 8 meters, will produce a 6 nanotesla anomaly. The maximum range can therefore be set to 8 meters and targets over 6 nanoteslas picked. Or it can be decided that a 6 meter spherical range is used, and then targets over 16 nanoteslas need to be picked. So this is quite a large anomaly. So as I stated, this is a terrible idea, but we're going to run with this anyway. Detection ranges and responses can be thought of as an ever-growing series of spheres, like a Russian doll, around the magnetometer, where the radius of the sphere is proportional to the response in nanoteslas for a given target. Now, dynamic coverage is the circular footprint created by the intersection of this sphere on the reference surface. So this is shown using subsequent points, but it's a simplified plot. In reality, the equipment is recording at least 10 hertz. These circular footprints are all overlapping. So now we're going to flip from 3D to 2D as it simplifies the visualization and is actually more realistic. So these magnetometers are recording at least 10 hertz, so we can think of the dynamic coverage as a series of circular slices as opposed to spherical segments. So in this image, the magnetometer in the center here is either coming towards us or moving away from us. We've decided on a 6 meter range, meaning that from our response curve, up here in the top right, we can calculate that we only have to pick 60 nanotesla targets. So the dynamic coverage at the reference depth is displayed in 2D in this green line, and in 3D it's also shown here in the corner with this green line. So dynamic coverage is a very simple calculation, just using Pythagoras, where the maximum range is the hypotenuse of the right triangle, and the other known side being the sum of the altitude and the depth of burial. This will allow us to calculate a dynamic radius at depth, which then needs to be doubled to produce our diameter. So as maximum range increases, dynamic coverage increases. As altitude decreases, dynamic coverage increases. But as depth of burial increases, dynamic coverage decreases. And it's this relationship between altitude, maximum range, and dynamic coverage, which means that if one is operating a survey and there is a push to complete that survey quickly, it can lead to decision making which may cut survey time, but will drastically reduce quality and validity of acquired survey data. We're now going to look at the situation where the maximum range is set to 6 meters, the depth to the reference surface at 2 meters, and the survey altitude at 3 meters. The dynamic coverage at the reference depth is shown with this green line. So we're running a survey, which means we have multiple lines of data next to each other. The desire is to ensure that the coverage at depth overlaps so that we can collect a complete data set. In this situation, that can be attained with a 6.6 meter line spacing between magnetometer tracks. But This is not fast enough for the survey operator. Knowing that at a lower altitude dynamic coverage will increase, it is decided to collect data at 2 meters altitude, but leaving all other parameters the same. In this case, a complete dataset can be acquired using an 8.95 meter line spacing. So now we're moving on to explanations of why allowing the surrogate items trial to lead these parameters is a bad idea. In this example, we're looking at a single magnetometer. So we're going to move on to TVGs and multi-magnetometer arrays later. But you will see when we get to those that this is actually still an applicable assumption. So in this example, we have a threat comparable target within the 6 meter spherical radius of the magnetometer. There will be a response from this target, and that response will be of the order of magnitude that requires that target to be picked. The magnetometer is omnidirectional, so upon gridding, the data required will plot this target at the magnetometer location. So this target will plot at this location in our grid. This target will also plot at this position in our grid. And a target located here will also plot at this position in our grid. Regardless of where the target is, the only data point we have is where the magnetometer is located. All of these targets are within the 6 meter range. All of these targets will plot at this position with a target response size that requires the target to be picked. So why is this a problem? It's a problem because the cross-sectional area of sediment, which is applicable and valid, is bounded by the dynamic coverage at depth and the depth of burial. If we can detect targets with the sort of response that we would associate with a threat item outside of this applicable volume, that actually doesn't do us any favors. It's a hindrance. So we can calculate that at a 6 meter maximum range, 2 meters altitude, and with a 2 meter depth of burial, there is a 31% chance that a threat-sized object will be located outside of your valid area, and instead will be inside these regions that you just don't care about and are actually causing you problems. So let's say that the survey contractor is really up against it and is so desperate to finish the survey as fast as possible that they are arguing for the maximum spherical range to be increased to 8 meters, meaning that from our response curve, a 6 nanotesla target needs to be picked. This allows for a gigantic range, 13.86 meters line spacing, basically halving the amount of survey time. So firstly, the data processors won't be happy, as there are orders of magnitude more small targets than there are large ones. Secondly, we increase the ratio of the cross-sectional area of invalid sediment to valid sediment to the point where it's actually more likely that a threat-sized target is located outside of the valid area than within it. And there are more of them, as the target threshold has decreased. Thankfully, there is a natural limit to this desire to increase spherical range, and that is reached at the point where targets can no longer be discerned from fluctuations in magnetic field caused by environmental conditions. So that's at about 2 nanotesla. Even in extremely clean data, you would struggle to pick a 2 nanotesla target. Okay, we're going to move on to TVGs. So 2 magnetometers in the array. We've got 2 lines at 2 different altitudes. One line at 2 meters altitude, one line at 1 meter altitude, and we're looking at a TVG. So there are 2 magnetometers in each of these lines. And these magnetometers will all have their own spherical ranges. We have a contact, which is between these 2 lines, and our dynamic coverage at depth is gigantic. All of our spherical ranges overlap. So we have no problem detecting this target. Or so the results from our sit suggested. Unfortunately, it's not as simple as we would hope. Firstly, because we have to grid the magnetics data to obtain anything useful out of it. Secondly, because of the orientation of the dipole. Thirdly, because of the way that we derived our spherical range. And fourthly, because our closest magnetometer to the target will not be recording the full anomaly, but will record a smaller response given that the sensor is offset laterally from the target. So we're going to start with part 4. I know it's confusing, just think of it as Star Wars. So in this plot, we have real samples shown in yellow, i.e. the magnetometer at that position has recorded a value for total field. Once the data are gridded, the blue areas will contain a value of total magnetic field that has been interpolated by a gridding algorithm. So we're looking at 2 survey lines, one's going away from us, one's coming towards us, and there are 2 magnetometers on each TVG, and the closest of that pair to a target on each line will produce a larger response than the furthest one. But that response will be smaller than the response recorded by a magnetometer that traverses directly over the target. So if this is our minimum distance, the magnetometer here has gone directly over the target, we will have a large response. We will get a smaller response with an offset line. The distance between the sensors in the array for a TVG is about 1.5 meters. This distance is short enough such that we can accept that the interpolated values created by a gridding algorithm are accurate. So we have two long ribbon-like snapshots of the total field, separated by a much greater distance than the sensor separation of the TVG itself. So now we're moving on to dipole orientation. And at the end of this, we're going to see how all of these problems combine to basically screw up the assumptions that we made during our sit. So dipole orientation. In the image shown, we have a nicely represented dipole. And there will be a peak and a trough of the total magnetic field residual associated with this dipole. And that peak and trough will possess a particular value at a particular offset between sensor and target. So all of the data used to resolve this dipole have been acquired at a similar altitude. And let's, for the sake of argument, state that this anomaly has a maximum peak residual of 10 nanoteslas and a minimum residual at the trough of minus 10 nanotesla. And we can draw an imaginary line through the peak and trough, and that is now our dipole axis. Now, moving into 3D, as it's the only way to visualize this, you can see that for any given pair of survey lines with a gap in the middle and a target in that gap, there is a continuum of different states with regards to the orientation of the dipole axis and the survey line, bounded by two end members. This is one particular end member. In this image, our survey lines orientation are parallel to the dipole axis of the target. Our dipole axis is coming towards us, moving away from us. Our survey line direction is coming towards us with this line, moving away from us in this line. But the line orientation is parallel to the dipole axis. This is actually the best case scenario, as will become apparent later. However, in this situation, our survey line orientation is orthogonal to the dipole axis. This is the situation you don't want to be in. But given that we are dealing with magnetics and most likely UXO survey, the assumption always has to be that of worst case scenario. So if we move on to the derivation of the spherical range from the SIT, production of the response curve involves picking from a grid of total magnetic field residual, generally with the array of magnetometers traversing directly over a target. The total response is the difference between the maximum and minimum recorded total field residual values of the dipole. So if you visualize this idealized version of a TVG line from a SIT, where one of each magnetometer pair has managed to exactly traverse directly over either the peak or the trough of the dipole, there will be an altitude, which is extracted from the survey data directly over the target. That becomes our spherical range. So let's say 5.5 meters, 5 meters, sorry. And the difference between the maximum total field residual at the peak and the minimum total field residual at the trough becomes the response. In this case, 10 nanoteslas minus 10 nanoteslas is 20 nanoteslas. Okay, moving on to gridding, the final piece of the puzzle. As I stated earlier, we have two ribbon-like snapshots of the total field residual, both offset from the target. This is assuming we have a TPG, and therefore producing a smaller than maximum response. The maximum response we would expect from one of these magnetometers being directly over the target. We are not in that situation. So we're going to have a smaller than maximum response on both of these lines. Because this is UXO survey, we're going to assume that the orientation of the dipole axis is orthogonal to the survey line orientation. So here's one of our ribbon plots. Here's another one of our ribbon plots. The survey direction is left and right. Our dipole axis is orthogonal to both of those. So we have no real data outside of these ribbons. So the peak and the trough of the anomaly, we actually cannot detect these. So we have no idea how large this anomaly may be because of that. In the situation that we're looking at here, we actually have a low value in 1,1 survey line, minus 5 nanotesla, produced from the negative pole of the anomaly, and a high value in the adjacent line, 4 nanotesla, from the positive pole, with a gap in between. So these total field residuals, as I stated, are smaller than the maximum and minimum because these lines are offset from the target location. So this is the reality of the situation that we're in. We have no real data in here, so we have no idea what's happening. The gridding algorithm itself is going to have to interpolate all of this. So this is the situation we're in with magnetometer tracks superimposed. So here's one TVG, here's another TVG. This is the situation. Down here in the bottom right, here's a schematic. So let's take this schematic and think about what happens during gridding and what we would expect if we had a more dense and richer data set, one which we could reproduce the entire anomaly with. So this is exactly the situation that we were just looking at, but in 2D from the side. So the survey lines are going away from us and towards us. So we're happy with grid interpolation between the magnetometers in the array. The question is, will we be happy with the interpolation between the survey lines? So the answer is actually no. And the problem is exacerbated with larger distances between survey lines. Common gridding methods and algorithms produce similar results. Minimum curvature gridding, or IDW, produces the same thing. The magnitude of the interpolated dipole will be as small as the gridding algorithm can produce within the boundaries of the user settings. This is because the curvature of the interpolated output is kept to a minimum. The curvature of this interpolated line in 2D will be kept to a minimum. However, magnetic field strength as a function of distance is a 1 over r cubed relationship for anthropogenic targets. Therefore, no gridding algorithm will ever be able to reproduce an accurate target response without also producing numerous false positives in areas where there are no targets. So what do we mean by that? Could we write a bespoke gridding algorithm that correctly represents a target response given data points from the magnetometer sufficiently close to record a response, but not close enough to fully reproduce the anomaly? So can we produce this red line from these data points? Yes, you could write an algorithm that produced that. However, you find yourself in this situation where you have no target here, and you have very small environmental or pitch roll related responses from the outer magnetometers, so 0 and a 1 nanotesla, and a 0 and a -2. These are not target related, it's noise related. You have now written an algorithm which is going to produce a target in this situation. Your real response isn't even this red line. Your real response is actually nothing, because as I stated, this is just noise. But your magic gridding algorithm that you've written is going to produce a target from this. So there's no way you can correctly represent the targets that are there, where you have gaps, without producing huge numbers of false positives. So here we have a relatively small gap between the survey lines. Let's say the contractor wants to increase the spherical range to get the survey done faster. So now we have more points that require interpolation by the algorithm. Our real data points are even further from the anomaly. This just makes the situation worse. It's going to produce an even smaller anomaly after gridding, but the anomaly itself could be orders of magnitude larger. So let's say that we're in a situation where the grid interpolation has actually produced a more representative anomaly than we would expect. So we have a target which is over our threshold and will require picking. This isn't a get out of jail free card, because at a large spherical range, it's still more likely that your target is within an invalid cross-sectional area compared to your valid cross-sectional area. Furthermore, you actually have a huge no data gap between these two lines, maybe up to 12 meters, maybe up to 14 meters if you have an 8-meter spherical range and a low altitude. So you actually have no idea where the target is located, other than that it is between the two outer sensors of these two lines. There may be stringent positional accuracy requirements associated with the survey as a whole. On a UXO survey, it's likely that there will be. The survey contractor may state a 2-meter positional accuracy for all data. If you have a 12-meter no data gap, there's no way you can position your target to within 2 meters in this gap. So now we're going to move on to real data, and this will help explain why all of these situations together create a problem. So this data were acquired by a third party and sent to Ocean Geophysics for processing. We're just looking at a snapshot here. There are actually 7 magnetometers in the array, and these are 2 survey lines separated by gap. Dynamic coverage was calculated for each of these lines. This is just 1 point on those lines, 5.28 meters and 5.15 meters. So providing our survey lines were 10 meters apart or less, give or take, we had full coverage. So 9.35 meters in this case. We were quite within our rights to interpolate this gap according to the SIT trial. And this is what was produced. Interpolated output. This is quite a large gap. We suggested that a survey line was shot to fill this gap, and that line was shot, and there was actually a target here. A target within the threshold for target picking. According to the SIT, this target should have been detected by the outer magnetometers. However, it wasn't. Or if it was, the response was too small for the gridding algorithm to produce the target here, which is entirely the point that we're trying to make. So these dashed lines are actually the survey lines that were shot. So this is the real output with this survey line added, the additional line. So here's the situation. This is technically in spec, given the dynamic coverage parameters that were determined from the SIT. But this is a more accurate representation of the total field residual. according to the SIT, both of these outputs are valid. However, the client's certainly going to want this one. This is a target which is within the threshold for picking, and it was completely missed simply using the parameters derived from the SIT. Furthermore, this is actually our best case scenario. Our dipole axis is parallel to our survey line orientation. So the fact that we didn't see this target is worrying. And this got us thinking. Given that the target should have been detected according to the SIT assumptions, is the issue with those assumptions entirely gridding, gap, and dipole orientation related, or is something else happening here? So we dug out a few old SIT trials, specifically ones where we were able to find a dipole that was well imaged from one pass of Surrogate Items Trial data over the target. And we produced a dipole axis through that target. And then we took this dipole axis and we offset this dipole axis and created virtual survey lines at half-meter intervals, 0.51, 1.52, 2.53 meters on either sides of the dipole axis. So now we're in the situation where our virtual survey lines are parallel to our dipole axis, which is exactly the situation we want to be in, best case scenario. And then we sampled our grid onto those virtual survey lines. This gives us a peak and a trough on each of these virtual lines and a response. So we were able to very accurately assess the altitude, as this is all from one pass of Surrogate Items Trials data over one target, and we knew the offset, which means we were able to calculate a 3D offset. And we had a response. And we were able to do that on both sides for all of our offset lines. So we asked ourselves where these results would plot on our response curve produced during our SIT. Now, for the assumptions from the SIT trial to be accurate, these would actually have to plot on our response curve. It's a 3D offset. So the assumption that we've made is that it's a spherical range. There should be no difference between a 3D offset calculated from an offset line using Pythagoras and an altitude flown directly over the target. Everything should plot on this curve. However, that is not what we found. We took one SIT trial, we calculated all of our offset lines and took the responses from those, and we found that these responses actually plotted lower than our response curve produced from the SIT trial itself. These were all picked from grid, directly over the target. These are all offset lines accounted for then with 3D distance calculated. So we thought maybe this is just a fluke. Maybe we just had a bad SIT trial. So we took another SIT trial and we saw the same thing. And then we took one more SIT trial using a real munition 250-pound bomb, and we saw the same thing again. And this is worrying because the entire assumption about dynamic coverage is based and predicated on the fact that this actually shouldn't occur. This should occur. Our offset lines, after accounting for 3D distance, should plot on our response curve the same response curve that was produced from picking from the grid from the SIT trial, but they don't. So the assumption is incorrect. This is why targets are not detected, even though they are within the spherical range. So we don't know why this is occurring. If we knew at this point, we would be writing a scientific paper. So to get slightly more relevant, as most of you who are experienced with magnetic survey would have noticed, who have really only dealt with single mags and TVGs so far, which are not particularly useful. With regards to UXO survey, we're going to move on to magnetic arrays. So in this scenario, we have 4 magnetometers within an array, each with a 6-meter spherical range. The whole frame is flying at 2 meters altitude. We have a 1.5 meter center separation. So we're in this situation from one survey line. So now we're looking at 2 survey lines. I'm just drawing the ranges of the outer magnetometers. These overlap at the reference depth, so we have full coverage according to our SIT. We want to minimize this invalid data volume. We also want to produce a cost-effective line spacing, whilst ensuring that no degradation of data quality occurs. Now, these annoyingly are antagonistic pairs. If our line spacing increases, our data quality will decrease. If we want to increase our data quality, we have to decrease our line spacing. There is no way around that. So how can we minimize this invalid volume? We can either increase our survey altitude and keep our range fixed, or we can decrease our range, or we can do both. So in our experience, the most sensible thing to do is come up with a sensible range. There is a reason why the larger UXO consultancies do not allow the spherical range to be changed, regardless of what is found in a surrogate items trial. Consultancies will state that the maximum spherical range you can use is 6 meters. You have to go and do a sit trial. If your sit trial shows that the target can be detected at 9 meters, they will not allow you to change this range. And this presentation is actually showing you the entire reason why this is so. So it's important to come up with a sensible spherical range and a sensible survey altitude. So in our experience, dynamic coverage diameter at reference depth should be no more than 200% of sensor separation. So a question we've heard before from a number of survey companies is, can we acquire the survey data at a very low altitude, 1.5 meters, 2 meters, and then upward continue our data to the point where the dynamic coverage at the reference depth is no more than 200% of the sensor separation? So the reason that they do this is that it helps them with infill at the end of the survey. In the last few months, it's easy to go to a client and state, we actually have survey data at a lower altitude. Our SIT trial suggested that we can use a much higher range and still produce full coverage. So it makes sense, but it's also a terrible idea. And the reason for that is because upward continuation works for infinitely long anomalies, or anomalies that fall off with a 1/r squared relationship, basically. It's designed for regional geomagnetic survey. So Sarah-Lee Sunderhay and Jack Brickhouse did a presentation at Oceanology 2024, where they showed that downward and upward continuation should never be used in UXO survey data outside of about 25% of the survey altitudes. So if your survey altitude is 2 meters, you can upward and downward continue 0.5 meter. So the reason that it's acceptable to do that is because over a short distance, the field drop off, whether it be 1/r cubed relation or 1/r squared relation, is comparable. As a processing step, however, it should not be used with UXO survey data. Point anomalies created by anthropogenic objects fall off with an approximate 1/r cubed relationship. Upward and downward continuation will not work and should never be used. Generally, fixed frames have lateral magnetometer sensor separations of between 1 meter and 2 meters. And the experience of ocean geophysics is that a target can only be fully realized with not more than one adjacent non-functioning magnetometer in the array. So that means you can lose a magnetometer, you can delete it, it's bad, its quality is terrible, it has an electrical fault. You can take it out. Once you've removed this from your dataset, you can still realize the entire anomaly if your survey line has traversed directly over an object. Once you have two non-functioning sensors, you start to miss things, which is why we state that dynamic coverage diameter at the reference depth should be no more than 200% sensor separation. In that case, you are in this situation. You just maintain full coverage with one non-functioning sensor. Ideally, if you want perfect data, your dynamic coverage diameter at the reference depth should be equal to your sensor separation. So you'll end up producing a grid of sensor separation. Your data will be perfect. You'll have a very small invalid data area. You certainly won't miss any targets. It's not going to be very cost effective. The only way to attain data quality that is this good is with accurate flying. Upward and downward continuation are going to produce errors. So this is perfect scenario. This is exactly what you want. But then dynamic coverage isn't really required. As stated, you're just surveying a grid of sensor separation. This is best case scenario. This is acceptable. 200% of sensor separation at the reference depth. Shouldn't miss anything. It should produce the cost-effective line plan for you. In conclusion, dynamic coverage is not a silver bullet that saves you survey time without any associated negative effect on data quality. A large spherical range combined with a low survey altitude will produce justified positional questions, may lead to targets being missed, and will lead to the detection of threat item type targets which are located far deeper than the reference depth or outside the survey boundary. Dynamic coverage diameter at the reference depth should be between 100 and 200% of sensor spacing. Upward continuation of data to ensure this is not recommended. Accurate altitude keeping will produce a high veracity dataset. Dynamic coverage diameter is more controlled by sensor separation than by the response of the expected threat item. It is a tool to calculate an acceptable survey altitude that produces full coverage and an accurate dataset. Dynamic coverage should be used in conjunction with a survey line plan, frame geometry, and maximum spherical range, all of which have been calculated using the expected response of a synthetically modeled target, not from Surrogate Items Trial data itself. Dynamic coverage should not supersede standard across-track and along-track gap analysis, but complement it. Thank you.